right? We're in the home stretch here at this point. What we've got is essentially 3, maybe 4 lectures on some of this quantum stuff, but we're not going to work anything super hard here. We're going to talk about a few fun results. We're going to go through some really neat things and get into some of the kind of the weirdness of physics, right? Get it away from a little bit more of our classical descriptions that we've been focused on this entire time and talk about some of the more modern stuff that shakes things up a little bit more than what we have seen so far. So, namely, one of the big hints that things are a little bit more weird beneath the surface than we expect them to be is light. Light's a really wacky one, and I've brought this up a few times kind of in passing. We haven't focused on it as any sort of real material quite yet, but light has a lot of strange things going on with it. Right, and let's talk about that. And really what I want to focus on here is essentially our history of how we have understood it this entire time. So I need to go into a slideshow because if you'll notice, we've got some nasty things going on with this one. So this question is really, what is light? And our understanding of this has changed quite a bit over time, right? This is not one thing that we have necessarily held fixed in the entire way. We've gone through a lot of different descriptions of light because it's been one of those things that we have seen, right? As long as we have had eyes, we have seen light. And trying to understand what actually makes that light because it's got all these weird properties. So at first, we thought that perhaps it's rays, right? And this is kind of going back a little bit of geometry review more than anything else. The idea here is that a ray, remember the difference between a line segment, a line, and a ray. The line segment is like a chunk of a line. A line is like an infinitely spanning thing. And so the ray is like one end of it is fixed, one end of it's not going anywhere, the other end extends off into infinity. And that was the idea, because how else do we see distant stars and things like that? So wherever the light source is, that's the beginning of the ray, and then it extends outwards forever. And we actually based a lot of equations on this, right? This was not any sort of small thing. We thought this for a very long time because realistically it worked. Most of our understanding of general linear optics is based off of this ray description. If you're wearing glasses, it's based off of this ray description, right? It was this idea that light travels as a straight line. And so as it travels, if we have different things in the way that can shape those lines, then we can do all sorts of things with it. Can light things on fire with a magnifying glass. You can use glasses or contacts to see. You have different telescopes, you have different lenses in your cameras to make sure that you can focus in things and zoom in and do other things like that. So lenses are kind of everywhere, and this description, ray optics, is still a valid description today. But the description of light using ray optics is not quite complete. And we always knew this because there were some slight things, the rays actually converged to this point. This is not actually an infinitesimally small point. Technically, there is a minimum band to a focus like that. So we knew something was kind of up, but we weren't sure if it was our just imperfect geometric optics or maybe something else was going on there beneath the surface. And here's again another description of different ways that we can use ray optics with mirrors in this case. Ray optics is unfortunately not something that we're going to be able to cover in this course, but it is a pretty cool thing, a very useful thing to have. So going beyond that though, at a certain point, we realized that light has some properties that make it seem a lot more like a wave. Right, and this actually goes back a couple hundred years at this point. Young's double slit experiment showed that basically if I take 2 beams of light and I allow them to kind of interfere with each other, right, like any regular traveling waves would, then I get an interference pattern that exactly matches what I would see had I been using waves. So these are 2 examples, and we'll get into each of these specifically today. But the general idea here is that if there is some sort of slit that a wave passes through, then it creates this wave pattern. It kind of blooms out because of those barriers. They cause a little bit of drag on the edges of this thing, and you get a bloom effect as the wave tries to travel through that. So, and we saw this, and that was essentially distinct evidence that light must be a wave. And indeed, you can split this thing up into different sorts of rainbows. This is the rainbow effect that we see, and I'll talk about again. This is kind of a preview of a lot of the things that we're going to be seeing today. But this is really definitive evidence light must be a wave. And we understand that. But the question started to come up. Okay, it's a wave. Well, sound has air that it travels through, and water waves has water that it travels through. what does light travel through? Waves need a medium, right? And I know when we were talking about traveling waves before, I said most of the time they have a medium, but not always. And the reason that I said most of the time they do is because things like light kind of screwed it up. Everything had a medium, or everything needed a medium, until light. And then once we understood light, that kind of messed everything up a little bit more. But really, what gave this away, that light is more than just a wave, was something called the photoelectric effect. Here's the idea, and we're going to get into this a little bit more as we go on, so this will make a little bit more sense. But the general description is that the energy of light depends on the color. That is, red light has less energy than violet light, has less energy than green light, right? It spans through the rainbow like that and then kind of goes beyond that. We'll talk about those. But there was this interesting phenomenon where if we would shine a violet light onto a piece of metal, then electrons would fly off and generate a current. And that's where the photoelectric comes from. Photo is in light, electric is in electricity. But okay, so if violet light that is low intensity is able to generate electrons, then surely red light at high intensity should produce the same amount of energy, right? It's a wave. So if I just put more of it in there, then that should work just fine. The energy is really the important thing here, because what's going on is I'm trying to ionize away these electrons. High energy, either way should work just fine. It shouldn't matter what color I've got. But it turns out it doesn't matter how bright you make that red light, we never see electrons. But once we hit a certain threshold, there's a certain color that once you hit that color, suddenly electrons start jumping off. And then once you have hit that threshold color, you can ramp up the intensity of the light to ramp up the number of electrons, or you can ramp it down to get fewer and fewer electrons. But the point of it is, you have to meet a certain color threshold before you start actually ejecting electrons. You have to meet a certain energy threshold to start ejecting electrons. And this idea maybe doesn't at first fly in the face of the wave description, but the general idea here is that a wave, low energy versus high energy, it shouldn't matter what the frequency of the wave is. The energy of the wave, you can ramp that up with the amplitude. You shouldn't need to have a certain frequency to make that happen. The only explanation for this difference is that light must be a particle. That's the only way this makes any sense. Because if light is a particle, then those low energy particles, doesn't matter how many of them there are, they'll never be enough to strip away the electrons. But high energy particles, even if small in quantity, could indeed, one single high energy collision would be able to eject one single electron. More high energy collisions, more electrons. But a bunch of low energy collisions would never be enough to ionize the electrons in the first place. It doesn't matter how many of them we would see. So this was a little bit of an issue, realistically. And now it's not that we have removed the understanding of waves. We still use waves as a description for light. It's just we also use particles. Light is both, and neither, kind of at the same time. But for right now, we want to focus a little bit more on this wave description, because we're going to dive into the particle description a little bit more as time goes on. Right now, we just want to focus on the wave properties of light, go through all of our evidence for this, all of our understanding for this, and then when we get a little bit more into the chemistry of things, we can talk about the particle side of light. But anyways, let me back out of this because a little bit easier to just leave on this stuff now. So as I was saying before, light exists on this kind of spectrum that we have. We know of the rainbow, of course, but light goes far, far, far beyond that, right? All the way from the gamma rays of supernova down to the very long radio waves that make up AM radio, all of that is on the span of what we call light. What we understand to be visible light is just one particular region of this full spectrum that our eyes are actually sensitive to. And this particular region, as we are going to talk about in a little while here, is essentially a band of color that doesn't interact with atmospheric light nor water. That is, these particular colors of light that we're able to see because the other things surrounding us, the air surrounding us, doesn't actually interact with that light. The air might interact with infrared light. It might interact with ultraviolet light. But the particular region that we call visible, it doesn't interact with that well, so we're able to see through it. Waves, of course, have this relationship between their speed, their wavelength, and their frequency. But light is a bit special because its speed is a constant 3 × 10⁸ meters per second. And that means that we've always got this consistent relationship between the wavelength and the frequency. And so some of these values are going to be a little bit more unique from what we've been seeing with sound waves, right? Sound waves can be like a meter long or something else like that. But most of the time, as we're going to be looking at light here, we're primarily going to focus on things in the like single-digit micrometers, a lot in the hundreds of nanometers, and that means that a lot of our frequency values are going to be 10 to the 14th, 10 to the 15th, right? Terahertz kind of frequencies here. So pretty large versus a lot of the frequencies that we've been seeing so far. You know, just have a sense of where those numbers are going to be. They're quite different from what we've been looking at so far, but the equations for waves, traveling, all that good stuff, nothing changes. So let me talk about that single slit diffraction that I was talking about, right? This bloom effect. What happens when we go through a gap? We get diffraction. Realistically, there's kind of like a little bit of a drag because of that barrier there. Each wall has a little bit of a drag acting on the wave trying to travel through, and so that when the wave X's out on the other side, it blooms out spherically rather than just continuing straight forward as it would. Depending on the size of the gap, how much it blooms in that sense will be a little bit different. A small gap, you can see it's a much tighter circle going all the way through. A large gap, on the other hand, doesn't appear to have that significant of a difference. So, and this also does depend on the wavelength, right? The wavelength is very, very important for how much of the gap or how much of an impact the gap actually has. But light shares this characteristic because light, as with water waves, is a wave. So, what do we actually get when we do something like this? We get this very unique pattern of a very single bright spot in the middle. We expect that. But then we get like a dark, bright kind of signal outside of that. And this one's a little bit unique. See, what's happening here is, just as we talked about last time with interference, we can get interference of traveling 2D waves. And for all intents and purposes, let's consider this just a traveling 2D wave like water or anything else like that. Well, there's a slight difference between either end of the barrier, of the slit. So what we've got here, we have laser light being shined, and we have this single slit. It's a gap A. So it's a really, really tiny gap. It's like a little pinhole that light is allowed to travel through. And it has a slight difference between either side of this. And because of those slight differences, you actually get this diffraction pattern is going to be overlapping and interfering with itself. It's not just a singular wave coming out, but actually kind of a series of waves combining together to create this weird lumpy pattern. And this lumpy pattern has these spots of destructive interference. See all of these dark bands right here, right? And I'm highlighting in spots that are already dark. So what I'm really meaning to say here is these spots and these spots and these spots and these spots. All of these spots are where we get destructive interference because of that diffraction. And we end up with a dark spot where otherwise we should be expecting to see essentially a pretty broad light region. So we actually have fancy equations that tell us exactly where those are going to be. I'm not going to necessarily go through or worry about how we derived these or anything else. We can just essentially use these equations. So the light comes in with a wavelength lambda, right? And I've got it kind of shown right here already. It's going to create a bright spot right smack dab in the middle. From there, we talk about each of these dark spots. So the first dark spot from the middle, P is equal to 1. The second dark spot from the middle, P is equal to 2. The third dark spot from the middle, P is equal to 3. So on and so forth. It should go infinitely out. And then that applies to either side. So P1, 2, 3, P1, 2, 3 on the bottom just as well. We have essentially diverging from the horizontal line right smack dab in the middle. Where are each of those dark spots going to be located in an angular sense? An angle diverged from that horizontal. We've got this equation right here. That is to say, if we want to know what the angle of the first dark spot is supposed to be, we plug in P is equal to 1, lambda, and then the width of that gap, A, and we get that angle location. We can do it for P is equal to 2, P is equal to 3, P is equal to 4 to find where all of those should be. We can also, I'm going to focus here on the bottom equation, find where they should all be location-wise. So this is a measure in meters, some sort of distance like that. So again, taking our dotted line as essentially our reference point, call this y is equal to 0. Then each of these dark spots will be located some distance y given by this equation, where L is our separation between the slit and the screen behind it. But with all that, we can plug in NAP is equal to 1, 2, 3, 4 to find the location of every single dark spot. The last thing that we've got is this width. And this width is really just kind of a result of this bottom equation anyways. Really what it's doing, it's looking at, okay, so we have this really bright spot in the middle, and it's kind of neighbored on either side by these dark spots. What is the distance between those dark spots? Notice here that it really is just essentially the distance of 1 and minus 1, add those up together. So it's not a super special equation all by itself, it's really just kind of a result of using the y equation on the bottom. So I want to take this. So keep in mind, all of these are essentially of dark spots. And I'm highlighting that in particular. I want to try this out in a problem because I think that's one of the best ways to get some experience with this. Let's try this. Let's imagine light of wavelength 600 nanometers illuminates a single slit. So single slit diffraction, just as we've been talking about. The intensity pattern shown, this thing that we've got down here in the picture, is 2 meters behind the slit. L. What is the width of the slit? Take the next 3 or 4 minutes. Because not the number of screens is which dark spot, right? The screen is just one big stretching piece where we're going to see all of these light spots, dark spots, the entire diffraction pattern showing up on it. P is which dark spot am I looking at? The first, the second, the third, the fourth. It's just picking out which one of those we're looking at. It is some integer number representing which one of these do we want to look at. Take the next 3 or 4 minutes. Find what is that slit width. Let's go ahead and start taking a look here. So here's what I'm thinking. Based on this graph, I've got a couple pieces of information that I could pull immediately. I could try to pull essentially the spacing of any one of my dark spots, but I think kind of the most telling thing that I'm seeing right here is dark spot on either side of my main peak. That distance between the two, this width, W, is 1 centimeter. So, and I have a special equation specifically for that width W, right? That is 2 lambda L over A. In this case, I'm looking for A. I know that L must be 2 meters. I know that lambda is 600 nanometers, but I need to be careful with all of my units here, right? I've got a lot of different lengths all kind of playing into each other. So I've got this width in 1 centimeter. I've got the length in 2 meters. I've got wavelength in nanometers. And what am I going to get out of A? Right now, who's to say? The easiest way to do this one is to take all of these units, put them all into meters, and that way every length you get is going to be in meters. Just make it nice and easy. If we need to convert it later, we can worry about it later. Right now, I think it's easiest to convert everything into meters and then deal with it then. So that is, L is just going to continue being 2 meters. Lambda is going to be 600 times 10 to the negative 9th. I know we can convert that into proper scientific notation, but it's probably just easier. Just multiply by 10 to the negative 9th. Your calculator doesn't care. And then, of course, my width is going to become 0.01. When we do something like that, now all of our units are in meters. We shift the order of some of these things. A will be equal to 2 lambda L divided by that width. Plug in all of our numbers in meters, and what we end up with is something like 0.00024. And we made sure to keep everything in units, or in meters, in the same units, I should say. So that comes out to be in meters. Convert it to millimeters, just take away 3 of those zeros. A should be equal to 0.24 millimeters. Yes, the width is only between the two closest dark spots, because realistically, after the first, so like right here in the middle where P is equal to 0 would be, is a bright spot. So like the bright spot kind of ruins the pattern, but going further than that, every single dark spot is evenly spaced. So all of the dark spots on the top, all of the dark spots on the bottom are evenly spaced. It's just the two in the middle, the two closest to the center, are off by a little bit. They're double what every single other spacing should be. So that's why W has its own kind of equation here, because it's the only one that screws up the pattern. Everything else is equally spaced apart. Because I can always take essentially the difference between 2 and 3, 3 and 4, 4 and 5. All of those are always going to be lambda L over A. The two middle ones just mess it up. Feeling good on that? Okay, so while I'm on this slide, I want to highlight one more time. These equations, as we see them, are for dark spots in the single slit diffraction. And I'm highlighting dark spots in the single slit diffraction because when we talk about double slit interference, now we focus on bright spots. Notice, we have a new variable keeping track of where these spots are as well. The bright spots are all represented by M. But it's again, just which one am I looking at? Am I looking at the center one, 0, the first one, second, third, fourth, going on and on and on. M can be any integer, and it's just telling us which of these away from the center am I looking at. But specifically, M is focused on the bright spots. P is focused on the dark spots. And we focus on them a little bit differently because, again, the single slit diffraction pattern is quite a bit different than the double slit diffraction pattern. The double slit diffraction pattern, this is a little bit of a strange one. So now we're focused on essentially the spacing between the two slits. Now I've got two slits existing, but I'm focused in on the spacing between them. And just like we saw with traveling waves, when I have two traveling waves interfering like this, where their peaks line up, I get a resulting peak. But it's not like fully constructive, fully destructive anymore, right? Remember that we've got now essentially certain particular regions that are going to be constructive interference. If we look at this video on the right, focus on where the peaks overlap. I see the peaks overlapping right here, dead in the middle. I also see a spot out here. I also see a spot out here. Going downwards. That wasn't a very clean line. Let me try that one more time. Going like this, like this. Those are all 5 regions of constructive interference that I see. The destructive interference are where I'm going to see essentially peak, trough, peak, trough, peak, trough, overlapping each other, specifically in between these other spots, like right here, right here, right here, and right here. Those are all destructive interference regions. And because of that, I end up with this large band structure. Right, now notice there's a little bit of a distinction between what we had with the single slit diffraction and what we're seeing here. Because in the case of the single slit diffraction, we said, okay, the main peak is like really wide, and then all of the dark spots after that are equally spaced apart. Whereas in the case of the double slit interference, everything is supposed to be equally spaced. Now, let's try this with a concept check real fast. Let's imagine you're doing some sort of laboratory experiment where you've got double slit interference, and that's the pattern that you see from the double slit interference. And then you block one of the slits. What do you see now? Which of these patterns do you think we're more likely to see? Okay, a handful of answers so far. So, we run into a little bit of an interesting issue. I'm going to say, right off the bat, I don't expect it to be B. See, if I block one of these slits, then what I should be getting is at that point single slit diffraction. B is double slit diffraction if I cut it in half, if I blocked one half after the fact. That's not what I'm seeing here. I would continue to expect to see, I would see stuff going over across the entire screen. So I'm going to say B is out. B is one of the ones that I definitely say, I don't think so. Now, the other ones here, you could make arguments for. And this is the kind of thing, this concept check is a little bit of a trick question. It's a little bit of a trick question, and that's why it's not one of the in-classes or anything else like that, because I really wanted to use this as a discussion piece more than anything else. Let's go back a little bit. Before I come out with a full answer here, let's go back to a picture that we saw from before. And let me highlight something that we didn't talk about the last time we looked at this, or rather the first time that we looked at this. Slideshow from current slide. We got to skip through all this nonsense. We don't care about that, This one. Look at what's going on here in the double slit diffraction pattern. Do you notice something strange? I notice a dark spot right here. It's not completely dark, but it's certainly a lot darker than the stuff to the left of it. Right here, I've got like a small, it's very dim. I'll do that kind of symbol to say kind of dim, but over a little bit more to the left, then suddenly we've got a little bit more of a bright spot. Why is that? Does anybody know? Does anybody have a guess as to why do we see a bright spot to the left of this thing? I thought all of these were supposed to be evenly spaced, and then maybe like a Gaussian or something for the intensity? Why do we see dark, then bright? Any guesses? The answer's actually right in front of us. Another trick, unfortunately. What happens here is, if you notice directly above us, it's the same single slit diffraction pattern. Yeah, the single slit stays there. The single slit diffraction pattern doesn't actually go away. It's still there causing problems for us. So what we're actually seeing here in the double slit, so here's kind of the crazy thing about this. What we're seeing in the actual double slit diffraction pattern is the interference of the double slit diffraction with the single slit diffraction. Right? That's the actual result we see here. We see all of these little splittings because that's the actual double slit diffraction interfering, the superposition of the two interference patterns together. Which individually, the single slit interference pattern is a single slit interfering with itself. The double slit interference pattern is two slits interfering with themselves, and then what we actually see is the interference of those two interference patterns. So there's a lot of pieces kind of all lining up here to get this exact picture. But one of the things that I do want to highlight on this is that notice the size difference between them. Notice how frequently we see dark spots in the double slit diffraction pattern, and how much larger the single slit diffraction pattern is than that double slit diffraction pattern. And that's something that I'm going to highlight here. But this is not actually one definitive value is the biggest problem. There's not one particular value that's really determining what either one of these are, because as we know, the single slit diffraction pattern depends on the size of the slits. So if we're going back to our actual question here, keep annotations, no, get those out of here. If we're actually going back to this thing, arguably, I don't have a lot of information about how large I expect these to be. So I could see an argument for either A or C. I think both of those have a somewhat reasonable argument that says, hey, well, we don't know anything about the diffraction pattern. We don't know anything about the slit size. And because of that, the spacing of these dark spots from just the single slit diffraction could be anything. And I would agree with that, with one exception. What's the issue with that description? What's special about the single slit diffraction that is different from the double slit diffraction? It's the fact that not all dark spots are evenly spaced. Most of them are, but the very middle two are just a little bit wider than everything else. So if I'm looking at patterns A and C, I see all of my dark spots evenly spaced. That's not single slit diffraction. So while there are arguments, A is kind of like a maybe, C is kind of like a maybe, I could understand where that one's coming from, but I don't think I would see those. I'm going to say probably not either one of these. It's probably D. The only problem is we don't see the full picture. If it is indeed D, then what I'd be expecting is another bright spot over here, and another bright spot over here, and another bright spot way out here, another bright spot way out here. We just simply don't see that on the picture. The answer is D here, because there is a size difference between these two diffraction patterns. But it's more D because none of the other answers work. D is the only reasonable answer that could possibly fit into this, just based on the slit size. But again, there's not enough information to definitively say. If somebody had presented me with D but shrunken down so that I see a really bright spot and then, it follows that single slit diffraction pattern, I wouldn't be able to say whether it was D or that new answer, because that size depends on the slit width. Does that all make sense so far? Do I understand where we're kind of coming from with this? This is a process of elimination more than anything else. We know it can't be A, B, or C, so it has to be D. But D is just a possibility. It's the only answer left. It wins by default here. But had there been another single slit diffraction pattern, I would not have enough information to answer this. Okay. So, let me highlight the size difference just a little bit more and really talk about where that comes from. Because if you notice here, very similar shapes probably are going to result in very similar equations describing them, or rather be the result of. Notice that we've got two equations that look extremely similar to what we just saw with single slit diffraction. Extremely similar. Right now, the difference again is dark spots for a single slit versus the bright spots of double slit. And one of the ways that we try to highlight that difference between the two is using M for bright spots versus P for dark spots to try and keep those as separated as possible. But what we're seeing here is essentially a difference in path length. Now, this is an experiment that you can run. You can actually run both of these experiments from home. Last year, I had tried to do this with a demo. If you see, I've got my laser up on that little cabinet right there. I have tried to run this demo before and show it, but it doesn't work so well, unfortunately. My webcam is not any good at seeing this. In fact, many of the cameras have a kind of tough time with laser light. It's a little bit difficult to see just because of the speckle effect. There's just a lot of kind of waving around. Like, even if you notice, so I've got a picture a little bit farther on down here of what these two patterns look like. Single slit versus dark slit. And notice that even like on a regular wall like this, they're just so messy. They're really blurry. And this is like a still image picture of this thing. A video just does not do well, unfortunately. But that's all right, because you can set this up with just about any laser. And what do I mean by any laser? I mean a $10 laser pointer is more than enough to get these kind of patterns. Take a sticky note and an X-Acto knife or scissors or something else like that. Cut some slits into that sticky note. Best effect might be to use a couple sticky notes all together, like use 3 of them or something and cut the hole through that. If you shine a laser light through those slits in the sticky notes, you will create these patterns. And you can see all of these effects for yourself. You can prove with a household laser pointer that light indeed must be a wave, because you get wave diffraction patterns from it. I really do highly encourage you to check this one out. Try it for yourself, because it's a super cool thing to do. I love this one. I really do. It's got a close place in my heart, because questions just like this one are what first convinced me to go into science in the first place. I didn't know what kind of science at the time, but it's where I got into science in the first place. So I really do recommend. This is an easy experiment to set up. You've got more than enough tools. If you don't already have a laser pointer, you can find a $10 one, and that works perfectly fine. But really what we're getting at here is, by using a laser light, one of the things that's special about a laser, this doesn't work with a regular flashlight. Right? Your phone flashlight or any other handheld flashlight or anything else like that does not work because it's not coherent light. The important part of this is that a laser has specifically the phase difference between either of these two openings, the sources of our waves, is 0. That's a result of laser light. So when we're doing this, as we are sending this light in, we can run into a little bit of an issue in that there's no interference as a result of a phase difference between the two. Any interference must be because of a path difference between the two sources, right? Going back to that delta R description. Remember delta R? Let's think about it like this. If there can be no phase difference between the two pieces, or no phase constant difference, then any phase difference that could be the cause of interference must be coming from K delta R. K is supposed to be 2 pi divided by lambda. And if we plug in specifically here, whatever delta R needs to be to make this thing work, well, it must be sum m times lambda. The lambdas will cancel out, and we get some factor of 2 pi, our baseline for constructive interference. 0, 2 pi, 4 pi, 6 pi. Any of those will result in constructive interference. The dark spots are then when my path length splits that difference, and we end up with some of the odd factors of pi. Pi, 3 pi, 5 pi, 7 pi, so on. And so we land with these equations and this description of the spacing of where each bright spot must be. Just like we saw last time. Theta is essentially my angle from the horizontal. Where is that bright spot angle-wise? Y is where is that bright spot distance-wise. So all of these distances right here, for example, if we're focused on the third bright spot from the center, then I would call this theta 3 or y3, and I would be able to plug in m is equal to 3 into these two equations to find those numbers. But now d is the distance between the slits, and the assumption here is that the distance between the slits is probably going to be larger than the slit widths themselves. And in that case, that's where we end up with the double slit interference is a much smaller spacing than the single slit interference, because they're mostly the same equation, right? It's still something like this. Integer lambda L over distance. But if the distance d is much larger than the width a, then the double slit interference is going to be a lot more tightly spaced than the single slit. Do we all feel all right with these descriptions so far? Are we feeling good? All right. So, concept check for everyone here. Let's imagine a laboratory experiment produces a double slit interference pattern on a screen. The point on the screen marked with a dot is how much further from the left slit than it is from the right. And we're talking total path, not just a horizontal distance, total path. What is that difference between those two slits? Think about it for a minute or two. See if you can come up with a good answer here. I only see one guess, but I'm not that surprised. I think the last lecture was a little bit unsure about this one. We started to get some guesses as we started talking about it a little bit more. All right, I like to see those. So let me start with this. Let me start with a description of what's going on in the middle. So first of all, we know if we have the central maximum right here, this spot right dead in the middle is m is equal to 0. And then we have 1 and we have 2. So we're at the m is equal to 2 is the one that we're most interested in. Now, looking at the spot right in the middle, can we all agree that should be equidistant from each slit? Right, the bright spot in the middle, it's essentially symmetrical on either side. I can't draw a straight line with this, but it should be something like this and something like this. And imagine those two line up right on the bright spot. But if it's smack dab in the middle, then it should be equidistant from either slit. Now, we know that can't be true for all of the other spots, right? Because there's only one middle. Everywhere else is going to be some difference of distances between them. But the condition here that we are getting a constructive interference when k times delta r is some factor of 2 pi. M times 2 pi. That is specifically k is 2 pi divided by lambda. So let me erase this. Let me move this over a little bit more. K is 2 pi over lambda. If we plug in that the difference delta r is equal to 0, then it's constructive because it's one of the even intervals of 2 pi, right? 0 works just as well as anything else does. But for everything else, we only get a bright spot if we are some factor of the wavelength away. That's the only way to get this expression m times 2 pi. That is, if we know we're at m is equal to 2, we must be 2 wavelengths away. This delta r is equal to 0. This is where delta r is equal to lambda. This is where delta r is equal to 2 lambda, and so on. What if we put the spot on one of the dark spots on the in-between? The dark spots are splitting all of these exactly in the middle. So if all of these spots as we're seeing them are supposed to be essentially integer amounts of the wavelength away, then if we are on the dark spot, for example, if we, let me put it right here. If you can see that dot, then that would have been 2.5 away. All of the dark spots are where we're getting one of those odd values of pi, 3 pi, 5 pi, 7 pi, and so on. So we'd be exactly half of a wavelength of separation. But they're all very evenly spaced, which is much nicer for solving, right? Rather than some exponential or anything else like that. It's much easier for solving with what's going on with that. So, whoops, I wanted to talk about this just one more time. Again, this is one of those things that you can set up at your own house or wherever you're at right now. This is a very easy to set up experiment. It is very fun. This was one of the things that I actually first heard about this in high school and tried one of these experiments in high school. And for anybody interested in this, it's a very cartoony video. It only takes about 4 or 5 minutes, but there is a wonderful video called Dr. Quantum and the Double Slit Experiment. And it is a cartoon video that single-handedly, I think, convinced me to go into science in the first place. It bothered me so much that I just had to spend 6 years to get a master's in physics. There's some really cool stuff here, is really what I'm trying to say. It is not a small thing. I think there's some very interesting things going on here. Highly recommend trying some of these things for yourself, because these are very accessible experiments. So, I want to try one more of these. Another question here. Let's imagine you've got a double slit experiment already set up, and you have been doing this with 630 nanometer laser light. You have measured the spacing between all of the bright spots. Every single bright spot is 1.8 millimeters away from its neighbors. What if we take the exact same setup and replace our laser with a 420 nanometer laser? What spacing will we see then? Take the next 3 or 4 minutes, see if you can come up with some answers for this. Then we'll talk about it together. So let's go ahead and start taking a look here. So we do have some particularly fun colors picked out here, because 630 is right around orange, red, orange. 420 is right around blue, violet, kind of color like that. So we can color code our answers just a little bit better here. But here's what I'm thinking. We have bright fringes spaced 1.8 millimeters apart. That is, if we were to look at this graph right here, every bright spot is 1.8 millimeters away from its neighbor. So what's the easiest comparison to make? What if we just take 0 and 1, the very central spot right here in the middle, and then the very first one? Then we know the spacing of the very first one should be at 1.8 millimeters. So let's write it out like this. Y of 1 being my wavelength. Well, and I guess I should plug in m here as well. M is equal to 1. My wavelength, L, divided by D, the spacing between the two slits. This should be equal to 1.8 millimeters. Fantastic. Now, here's an issue though. We don't know L, we don't know D. We have 2 unknowns in one single equation. It's not solvable. And there's not actually anything else to help us out here, right? There's really only one equation that we have for all these spacings. The angle equation doesn't, it just says the exact same thing. It doesn't actually help us at all for finding these values. The angle equation is kind of meaningless for us. So we're kind of out of luck. We really can't solve out for either one of those values from this experiment alone. But what we can do, let's think about it like this. Let me specify wavelength 1, lambda 1, is equal to 630 nanometers. Call wavelength 2, and let's shift our color for this, so let's do a violet for it. Wavelength 2 is equal to 420 nanometers. Now, let me look at the exact same equation, because we're trying to find the same thing, right? We're trying to find, essentially, if we find y1, then we know that is the spacing between every single fringe. So, y1 on the purple side of things would be equal to, again, 1 times now lambda 2 L divided by D, because no part of the apparatus actually changed. We didn't change anything else. We didn't change the spacing. We didn't change the slit width. We just changed which laser we were shining into it. So it's the same L and D as we saw before. And now we might have something on our hands, because we might not be able to solve out for either L or D, but we can solve out for L over D. Let's do it like this. Let me show you what I mean here. If we take this expression for y1, let me go ahead and move. So let's say y1 divided by lambda 1 is equal to L over D. y1 should be, let me convert this real fast, to 0.0018 meters. My wavelength, similarly, should be 630 times 10 to the negative 9th meters. We want to make sure that everything is in meters. And that's a really important deal here, because what are the units of L over D? Any guesses? What are the units? Is it like a watt? Is it a meter? Is it a nanometer? Any guesses? It's dimensionless. It's a distance divided by a distance. So that is the most important time that I need to make sure that my units match, because the units need to cancel out. I can't have nanometers divided by meters, because then I've got some nano nothing, right? I can't deal with that. So I need to make sure that all of my units coming into this thing are going to be the exact same units so that everything cancels out at the end of the day. Convert y into meters, convert lambda into meters. L and D, just call them both in meters because they're going to cancel out anyways. And when we take that, when we plug in all of our numbers like that, we get a dimensionless 2,857. Now we know that ratio. That ratio has not changed. When we go over to our purple laser, we plug that in with our purple laser, and what we end up with is right around 1.2 millimeters. Or 0.0012, which we then convert to millimeters. So how's about we keep moving right along then? So, there is a very unique piece of equipment that sometimes gets used in a number of different places, called a diffraction grating. And a diffraction grating is very, very, very cool because what it can do is that it can split up multiple frequencies of light. What it is essentially a double slit on demand. A diffraction grating will create this double slit interference in a couple different manners, actually, depending on the type of diffraction grating that you've got. The kind that you might be more familiar with is actually essentially a pass-through diffraction grating. But all of these things are essentially some sort of ridged structure, some sort of sawtooth structure of some sort that when light passes through it, you get double slit interference. So if you have ever tried on those glasses, there's, I know, like the paper or cardboard glasses that make everything diffract in all sorts of crazy ways and everything turns into a rainbow. Those are diffraction gratings. There's also a reflective type that works very well that I have used quite a bit myself. And you can use them for very, very cool things like tuning lasers. And those things in particular, what we would do is we would have a laser and we would shine that laser at a diffraction grating and then essentially use a set of mirrors to send it back into the laser. And in doing so, depending on how we turn that diffraction grating, we could essentially tune up what frequency we wanted the laser to be shining out. Which is much, much better than just trying to hope that the laser is on the right frequency. Because I think I've talked about this before. Atoms are very, very picky about the colors of light that get shined into them. So even the laser being ever so slightly off is enough to majorly impact what's going on in the experiment. But anyways, one of the common places that you can see these things used is essentially when you have a variety of different colors of light coming in and split them all out into different areas. And I talked about this, about like a monochromator, a certain device that's able to essentially take some sort of large signal, all of these different colors of light coming in, and split them out one by one and find the intensity of each one of these. Now, there's a lot of different places that this can end up being very useful. And one of these things, so this is just looking at two colors in particular, right? Notice the overlap. We've got like a purple here in the middle, and then on the outside, it splits into this violet and the blue. And this really is how we see most colors. It's just combinations of different colors of light, and this is how our eyes kind of interact with it. Purple is one of those colors that is not technically a real color, but it's a combination of violet and blue. But anyways, the other place that we've actually already seen this, in a sense at least, is, let me go back into this one right here, make sure that I'm all on the right settings so that we can actually see this thing. But in a sense, this is exactly what we see right here. You can do this with a single slit, right? It does work like this. It's just going to be essentially much more spaced out than you would see if you had done this with a diffraction grating or a double slit instead. But you can use the exact same idea to split up white light into all of the different colors, into the rainbow. And that's what water vapor is doing when we see a rainbow in the sky. It's acting as a diffraction grating that allows the white light from the sun to split into all the different colors. So, there's some cool effects from this thing, right? There's some really neat applications for a lot of these. But some of the ones in particular very much depend on what you're looking at. So, atoms, for example. Again, if you have ever had the opportunity to look at what different light atoms and compounds put out, there's some really cool patterns here, right? But notice what's going on with all of these is that they are very, very, very specific colors. Now, when you actually look at these things, like a neon sign, think about a classic neon sign, right? It's like this big, bright red-orange kind of hue. You don't individually see all of these color bands. You see the combination of all of the colors. If you were to try and measure out the light and just measure the intensity, for example, you would see all of the colors shining bright, and that doesn't tell you anything about what's actually inside of that. Maybe, if you're very familiar with different compounds, you have a little bit of a sense of what they look like. Like, I can tell the difference between like a xenon and a neon light, but that's really not a challenge because the xenon light shows up as white. So, there's a little bit of a discrepancy there. If you are experienced and have a little bit of knowledge beforehand, you might know what the individual colors look like. But let's say we're looking at some random mystery material. We want to know what it's made out of. What we can do is we can take essentially the characteristic fingerprint of every single molecule and every single individual atom. And if we shine the light on this thing and we look at all of the different colors that it puts out, we can characterize exactly what must be inside of that object. Now, part of the issue with this is that everything is very, very unique. It's a benefit and an issue, right? Because if you end up with something that's a complete mystery, if you have never seen this compound before, then it's not going to show up anywhere in any of our databanks of what colors we should be expecting. But if it does consist of compounds that we already know, then we can characterize it just like this. If you see a sign and you say, I don't know what that is, and you take your diffraction grating and you look at every single individual line of color, then you can characterize, you can say, hey, I see every line that makes up neon. I know this must be made of neon. Perhaps you see a mixture of the neon lines with the helium lines. Like you're looking at this and you see a lot of extra purple lines and maybe this extra cyan line. Then you can say, okay, well, this must be a combination of neon and helium. Now, if you look at something like water, that's a more complicated beast because molecules are much, much, much more complicated kinds of particles. So their emission spectra are wildly different from some of the individual atoms, but the main point of this is that it's essentially every material's fingerprint by splitting up all of these individual colors. But all of these are the result of what we call electronic excitation. Right? When we're talking about these lamps or anything else like that, those patterns that you see, those colors that you see are because there is electricity flowing through those materials. And what that does is that excites the electrons of those atoms to a certain level that they're allowed to then emit. Every atom has unique levels for its electrons, and that's why every atom has unique colors that it emits. It's why electrons won't really interact with those other random colors that show up because there's not anywhere for it to go. There's not a gap that exists that those electrons are allowed to transfer between. So atoms only like very, very, very specific colors when they are dealing with electronic excitation. And notice here that we show these things as essentially solid lines, but if you look at this thing a little bit closer, you can see that not all of the intensities are actually the same value. Like for mercury, for example, there's relative values. The red is a little bit less excited than the middle yellow and green and cyan. And then there's a little bit of a difference between the violets. So it's not necessarily, this is mostly saying what lines do you expect to see. Doesn't really, but these graphs don't say anything about the relative brightness. But let's go to this other picture that I've got here. The other type of radiation that you can get. And this is our thermal radiation. So this is actually an image of the different colors that the sun is putting out. Right? It's no longer just individual bands. Now we've got the full thing. Right? Just about every visible frequency we can see is being emitted here. Now, there are some slightly strange things that I do want to kind of highlight here. Notice that we've got essentially these like little dips in the emission. None of them are actually all the way at 1, but we have some particularly notable dips in the color here. And what those actually are again, essentially the fingerprints of what actually goes into the star. So I should probably leave those there for when I'm talking about this. They're the fingerprints of what's actually there in the star, though. Those will help us understand what actually must be going on inside of the star, the hydrogen and the helium that make up the majority of the sun as we know it. So even in the case of a thermal radiation, what we actually see from this thing is really kind of a combination between the two, the thermal radiation as well as the electronic excitation, because anything that the atoms might be absorbing, they're going to start absorbing and start to change some of those properties. But really, all of this thermal radiation is because all of these atoms, they're in chaos, right? And I feel pretty comfortable using chaos for this term because to say billions is a massive underestimate. Right? Think about how many a mole is, and then how large the sun is compared to a liter or something else like that, right? The sun is billions of moles is an underestimate for how many atoms are included in it. Every single one of those atoms is bouncing around, colliding with each other. Every single one of those things is, very nearly ionized constantly. Electrons can barely exist around it in the first place. They're just kind of constantly getting buffeted around in every single direction. And because of that, the light that they're going to be emitting is also very chaotic and very spread out. That is, anything with temperature, anything with thermal activity going on in it, that includes me, that includes you, that includes my desk, my mug with drips of cold coffee left in it, still are emitting this chaotic spread of light. And all of these things are doing so on a spectrum that we call blackbody radiation. So let me give you a little bit of history of this word first. A blackbody is generally, it started as a term for a perfect absorber. So a black hole is a great example of a blackbody because all light comes in, no light comes out, right? It absorbs all colors of light. Unlike the atoms, which only like particular colors. So, and that's the sense of what the blackbody term means. It means no light is escaping from this thing. No reflected radiation. Only incident, only absorbed. So the reverse of that, the blackbody emitter, is the object that emits all colors, all varieties of light. So the sun, despite these little dips, is a pretty good example of a blackbody emitter. Right? Most thermal objects are pretty good blackbody emitters. The sun just in particular, because it's got a lot more brightness kind of even across the board than, say, you or I. Because the human body is at a much lower temperature. And actually, what we see here, the radiated wavelength and the temperature of objects are very closely related. So when we're looking at the sun, for example, what color is the sun, realistically? Whereabouts? Yeah, kind of like a yellow color. I agree. Like anyone that says the sun is white, I'm like, well, yeah, but it's like not pure white. It's like an off-white, right? There's a slight yellow tinge to it. And the reason for that is because the maximum peak wavelength emitted depends on the temperature. See, when we have something with temperature, we actually get this, what we call the Stefan-Boltzmann distribution. And the Stefan-Boltzmann distribution tells us essentially For every single wavelength of light, how much of each wavelength is this object going to be emitting? So the sun is right around 5300 Kelvin, which we see peaks right around between yellow, green, and orange. Yellow, right? And then notice how substantially these drop off as you start to drop down in the temperature, right? All the way, by the time we're at 3500 Kelvin, we're already in the 800 nanometer range, which is what some would call near infrared, right? That's really stretching what our eyes can actually pick up at that point. So, and that's 3500. Where are we? Human body is 313 Kelvin or so. We're not here. we're like here, a flat line down here at the bottom. Technically speaking, the human body does constantly emit all of these different colors. Every one of us is a black body emitter. But the amount of each color that we actually emit is drastically scaled down from what we see from the sun because those temperature differences, right? The sun is so much warmer than us that it's going to be emitting all of these colors, shining this extremely bright light, whereas us, at the temperatures that we normally exist at, are nowhere near as bright because there's simply not as much temperature. There's not as much thermal activity, nearly as many collisions, things going on like that, that would cause that light to be emitted. So, two equations that I want to really focus on here, as we see them. First is Stefan's law, right? Which is basically saying the intensity of an object, the total intensity, all of the different colors of light wrapped up together, is equal to this constant, sigma, times t to the fourth, which is kind of unique. But the units for that, watts per meter squared, Kelvin to the fourth. Kelvin, the only temperature unit that science likes to use. Don't anybody even begin to mention Rankine. Kelvin is the unit that we like to use for everything. Kelvin's going to be the one that we need to plug into here, because if you plug in Celsius, things get a little bit weird. To go along with that, we also have Wien's displacement law, which tells us essentially where that peak wavelength is going to show up. Lambda max, the peak wavelength, times the temperature, is equal to some constant, 2.9 times 10 to the 6th, and the units are important here, nanometer Kelvin. That is to say, when I plug in a temperature in Kelvin, I'm going to get a lambda out in nanometers, right? Again, kind of going back to very early on when I was talking about some of the different units we'll see here. Oftentimes, we like to measure light in nanometers, so that's why that unit's there. So there's some really cool stuff kind of going on here, and there's a lot of information about this, but this is another one of those things that you can kind of see for yourself. All of these objects with temperature are emitting in a spectrum. There is not just one fixed value. Despite the fact that we do have a peak wavelength to it, it does emit in a very, very wide spectrum. That's why you can still get sunburn. Sunburn is not a result of visible light, but of infrared light. Not infrared, ultraviolet light. Infrared's the safe one. Ultraviolet light, over in this region over here, is higher energy. It's more dangerous. The sun doesn't emit as much of it as it does the visible light, but it does still emit a fairly reasonable amount, to the point that we need the ozone layer above us to actually protect us. And then even then, after it gets through the ozone layer, we still need sunscreen or else we're at risk of a sunburn. Infrared, on the other hand, is also a very significant portion of the sun's light. In fact, it's about like a 40 and 40 visible and infrared, and then the last 20 is made up of ultraviolet. And you can actually try this for yourself. Here's an example of this. Be safe with this if you're going to try it. But one of the cool things that I'll like to do sometimes, if I want to kind of remind myself of how cool there is just stuff everywhere that's really, really neat, I'll turn off the lights in my kitchen and I'll turn on one of my stove burners. And what you start to see is that after it starts to heat up, it starts to glow a very faint red. Now, don't do this for a long time because I don't know what happens. I know some stovetops are not meant to be turned on with nothing to take that heat above them. So don't do this for a long time if you're going to do it. Also because you're turning on a burner and that's not necessarily super safe. But if you do this with all the lights out, you can start to see that very faint red glow. And that's a combination of a couple different things. For one, it's going to be essentially that trailing effect of it's just ever so slightly starting to leak into the visible range for red. But also, if the infrared is bright enough, our eyes can kind of pick it up anyways. The red color cones on our eyes do an all right job with near infrared stuff. It's just it has to be a lot brighter for our eyes to actually pick it up in any meaningful way. You might not notice this when all of the lights in the kitchen are turned on or when sunlight's hitting things because that light is significantly brighter, right? It's kind of like looking for the stars during the day. The stars are there, but they're just so dim as compared to the brightness of the sun that you never see them. You can also do this, the oven does this particularly well as well, because that way you start to see kind of that red-orange glow from that as it gets up to a very high temperature. So, I want to try this on a problem. Let's imagine we have a 2 centimeter diameter metal sphere glowing red. And we're looking at this thing, and we find that the peak wavelength is right around 2 micrometers, not nanometers, micrometers. How much power does the sphere radiate? Take the next 4 or 5 minutes to work on this one, and then let's see what you get. All right, so let's go ahead and start taking a look at this. So here's what I'm thinking. We've got some sort of object emitting light, and what I'm thinking with it, more than anything, so I know it's kind of glowing quite literally red hot, right? Because 2 micrometers is getting there. It should be a visible red at this point, if not, it's primarily an infrared still, but it is starting to glow a visible red so that we can notice it. So let's just kind of draw it like that. Something like that. That's all these things that I'm trying to emit. Now, the amount that it's emitting, we're given this value as essentially the equation that we're given is intensity. And my question here is, what is intensity? What are the units of intensity? That really can kind of help guide our process. What are the units of intensity? Does anyone remember for this one? The units of this constant are helpful. It's watts per square meter. So for one, I love this constant. This is my favorite constant in physics. And I've been in physics long enough that I have one of those. Because it's 5, 6, 7, 8, right? It doesn't need to have anything other than that. I love it. It's easy to remember. It's wonderful to use. 5, 6, 7, 8. Rarely get something that nice. But the units for this were watts per square meter Kelvin cubed. Intensity is a measure of watts per square meter. Power per area. In this case, what is the area that I'm talking about? Where is this being emitted from? Is it the surface of the sphere? Is it the total volume of the sphere? Where? It's the surface, right? It has to be the surface because anything going on inside of it. If a photon is emitted from inside of the sphere, then it's just going to run into the next atom nearby. So the only way that the light is actually able to leave the object is if it's coming from the surface. That is to say, this thing A right here is the surface area of the sphere, 4 pi r squared. Because again, you might have seen the vein kind of bulge on the side of my head when I mentioned 2 centimeter diameter. No, nonsense. 1 centimeter radius. So we've got the radius, we can find the surface area. Then the power that we're looking for is just this P right here. P is equal to A sigma T to the 4th. We're almost there, but we don't actually have the temperature. Not to worry though, because temperature is related to the peak wavelength. We had this equation on the last slide that said peak wavelength times the temperature in Kelvin should be equal to 2.9 times 10 to the 6th nanometer Kelvin. Make sure that I actually got that right. 2.9 10 to the 6th nanometer Kelvin. So the last thing that I need to do is I need to make sure that I match that unit. I see nanometers. I'm given micrometers, which is not quite the same thing. Lambda is equal to 2 micrometers which should be equal to 2,000 nanometers. Now I have the correct unit. Now I say temperature should be equal to this number divided by lambda. I should get a temperature something like 1,450 Kelvin, which is actually pretty toasty, right? Depending on the metal, this might actually be a liquid ball of metal rather than a solid ball at this point. But that's all right. Now that we have the temperature, we have the surface area, we have the constant, we can find that the total power should be 315 watts. So, all of this stuff, I think, is just, it's really cool. If I'm being like completely honest and everything else, so much of this stuff is fascinating to me, and I've got a philosophy on my life that everything is cool if you know what's cool about it. There's so many neat things out there, like looking at why the burner glows the color that it does when you turn it on, and how you can relate that to the temperature and what must be going on behind the scenes there. And essentially, when I turn on the burner, there's suddenly like this massive release of all of this extra infrared radiation spreading throughout the house. Stuff that I might not even notice, but maybe my phone does. Maybe my Wi-Fi gets a little bit worse when I turn on that burner or something like that because of all of a sudden extra spewing of infrared radiation. I think about what's going on with the sky and why I can see through the atmosphere to see those clouds all that distance away and the differences of colors of light. How I perceive color is all a combination of different colors of light and how much is absorbed versus how much is reflected. I think there's fascinating things out there kind of everywhere, and I love this kind of material because it's so widely applicable to everything that we see. So really, I do encourage you again, some of these experiments that I'm talking about that are very easy to set up and very easy to do, try them out. They're really, really cool. I promise. You will not regret it if you see some of these things, especially for how cheap and easy it is. These double slit experiments, proof that light is a wave, one of the most complicated questions that we've got in physics, and trying to understand that duality, you can demonstrate that for $15. There's some really fascinating things out there if you know where to look. But that's all the stuff that I've got for today, team. Next time, we'll pick back up talking about more of the weirdness that goes into modern physics and the reality of the world. Thanks for being here.